Yeah, today is the fourth class of this of the course. Mostly we are well. So far we have been talking about fixed priority, and today we start a bit with EDF. Yes. So first I will just introduce some basics of EDF. EDF, the task model, is the same as with the one with fixed priority. So we have computational time CI, period TI, period of minimum interval time TI, and deadline DI. Right. So if in fixed priorities are per task. So basically all jobs of the same task have the same priority, while in EDF jobs are prioritized per job. So jobs are prioritized according to their deadlines. Okay, just the draw an EDF schedule. Yeah, maybe it's no big deal, but just to waste some time. This is the most typical example of EDF, I would say, because it shows where fixed priority misses a deadline and EDF doesn't. So yes, that's the good example. So if we have if we have fixed priority, now I'll do fixed priority. Fixed priority, we have something like this. And here we have a deadline miss because it has to execute for 3 time units. So here it executes for 2, and then the next one executes here. So here we miss a deadline, and then it executes for the others. Okay. So fixed priority miss a deadline for this task, while instead if we go for EDF, what happens? It happens that at this point this job is released. But this job has a deadline here, which is later than this deadline here. So basically, in EDF, this job at this point is higher priority than this one. So this job continues executing. So it executes here. Then this job is executed here. At this point, this new job arrives, but this job has a very late deadline. So this is higher priority. So we have this pattern. Okay, then at this point this guy can start execute. Then here what happened? Well, here we have this new job coming in, but these two jobs have the same priority, the same deadline. So I mean, in EDF ties are broken arbitrarily. So I don't know. We can maybe keep executing with some. This is for 3. Yes, keep executing this. Maybe it's a good idea. And then execute this. Okay, that's the basics of EDF.
Sorry, Enrico. So under EDF, with job that have the same deadline, ties can be broken arbitrarily, and all the
the point is that the point is that when the deadlines are coincident with EDF on single processor, ties can be broken arbitrarily. Okay. And if there is a deadline miss, it will be there will be a deadline miss for any way you break the tie. If there is no deadline miss, there will be no deadline miss in any way you break the tie.
This is not truly multiprocessor, right?
I think it's not, but I don't know. I didn't think about that very carefully. Okay, and this is EDF. Okay. Yes, why is interesting? It's interesting because if a task set is feasible, we are in uniprocessor, right? To keep in mind. So if a task set is feasible, meaning that it exists a feasible schedule, okay, then EDF, the task set is EDF schedule. So EDF can can schedule any task which is feasible. Okay. Then we have this theorem by Euler, which is that if we have implicit deadline, a question? No. If they have implicit deadline, is deadline equal to periods, then the task set is scheduled if and only if, then the condition of the utilization is true. Okay. The only if is always true because, I mean, this condition is necessary for having a feasible a schedule. On EDF is also sufficient, so I mean it's perfect. Okay. Right, this is kind of obvious. Any fixed priority schedule is also EDF schedule, yes, because this region, if you want to see it, the region, it includes the fixed priority, the region of fixed priority schedule task sets. Okay, now let's introduce this concept of demand-bound function, where the previous condition that we saw was for the implicit deadline case, with deadline equal to periods. In general, if deadlines are not equal to periods, the schedulability condition becomes a bit more complicated. Okay? And to guarantee a task set with any type of deadline, we have this the so-called demand-bound function tests. Okay? So basically, we say that the task set N is EDF schedulable if and only if this condition is true. This condition requires that for all t, for all time instance over time, the left-hand side here is called demand-bound function, okay, which is yeah, I'll draw it later. So this quantity has to be less or equal than the deadline, than t. It has to be true for all t. Okay. Basically, the demand-bound function is the amount of computation of jobs. Here, in fact, we will, well, let's see. The max, okay, this term is the number of jobs with release and deadline in 0t. Okay, this is the number of jobs with release and deadline in 0t. Then, if we multiply by CI, we get the amount of computation required by this number of jobs. Then, if we make the sum over all the tasks, we get this quantity over all tasks in the set. Okay. Okay. The notation typically is dBF of t. Is the yes, I wrote it here. It's the maximum amount of work of jobs with both activation, where here we use the word activation, and deadline in 0t. Well, the condition now is not per task, while in fixed priority the condition is per task. It requires that for all tasks, so you have to check task 1, task 2, task 3. Here the condition is all together. Why that? Because any task may influence any other task, depending on its deadline. So, that's why you cannot split schedulability on a task-by-task base. And yes, right. This max, the max with 0, is needed only if you have a deadline larger than period. This is quite so. But if for some condition, for some assumptions, you know that the deadline is always less than or equal to the period, then you don't need the max with 0, because this quantity, the floor, is going to be anyway greater or equal than 0. So you don't need to do it with max with 0. While if di is very large, as you can see here, di has a minus sign. So if di is very, very big with respect to t, then this can become negative. And that's why you may need to have the max with 0. Otherwise, if you remove the max with 0, you get the negative number of jobs, which is really not what we want, right? Of course, you can ask me questions anytime. I guess it is something standard. Okay, yes, right. So what's the problem here? The problem in the previous condition was that it is required to test for all t. And for all t, many values. Right? For all t, it maybe takes a lot of, well, it's not practical at all. So what's the point here? The point here is that we can observe, by observing how the dBF, the shape, in fact, if you take a look at this expression, basically this expression is like this. So, right, so it's a floor, right? So we start at 0, here we jump, here at some point, here we jump, at some point, here we jump, and so on, so forth. It's something like this, right? and we want this quantity to be true. I mean, we want this quantity to be below the line t for all t. It's quite, it's easy to prove that if the condition is true only at the points where the function makes a step, then it's true for all. Okay, that's quite simple to prove, because for any point here, of course, if it's true for all, it's also true at the point of the step. If it's true for the point at the step, then you can prove that it's true in all the points that are on from this step to the next step, strictly, so without reaching here. Obviously, right? What?
No.
Okay. Right. So how do we write? The condition with this new observation? Well, basically we can restrict to. Well, we need to add explicitly the condition of the utilization, and you can notice that before there was no explicit condition of utilization, because if you check for all t, you don't need. I mean, this implies also that the utilization is less or equal to 1. While here, since we are making the test over a bounded set, we need to require explicitly the condition of the total utilization to avoid that for large t, the demand bound function may go above t. Okay, so how do we write the set of deadlines? Well, we write it as it is. So the set D is the set of absolute deadlines dik, deadlines of task I, job k, where then dik is what? Is di plus a multiple of ti, where so then k is then the index of jobs, where I is the index in the tasks, and k is the natural numbers, all jobs. However, we wanted all deadlines to be less than some d star. D star is a sort of upper bound to the point where we need to make the test. And this upper bound is something that, in general, we would know extra information. It's proved to be, there is some, a couple of words trying to make this as small as possible. But on the first, approximation, let's say it can be set equal to the least common multiple of all the periods plus the maximum delta. Okay. Yes, right. Here it says, well, it's a bit ugly here. Maybe a bit ugly. Oh, it's not this. Check it. Right, so H is often with sometimes we denote the least common multiple of periods as H, and we call it hyperperiods of the tasks. Okay. Right, to reduce the number of points, one can do now. What's the good thing? Now this test is something that we can at least have. The test before we could not use, because for all t is an infinite number of points. This at least is a finite number of points, so we can implement it. But of course, it is interesting to try to reduce it as much as possible, to reduce the number of points as much as possible. Then, what can we do? Well, from the condition of upper bounding the demand bound function, that is the condition that. So now we have this upper bound function, right? With the demand bound function. Okay. So from by upper bounding the demand bound function with a linear function, let's say something like this, which is something that we can easily do by removing the floor here. By removing the floor here, we can upper bound. By removing the upper bound, then we can find this point that I call maybe this star, and then what we have? We have that for all dt larger than this star, the the test is automatically guaranteed because the upper bound is below t. So if the upper bound is below t, then the DBF is below t. So we don't need to check here. Well, we do need to check here. So basically, this is a way to shrink even further the set. So I mean, if you do the math, I hope if I did it correctly, you get this point with this expression. Now I have a question. What happened to this star? Because here in the expression, I have the total utilization of the tasks, and so which appear like u over 1 minus u, okay, times the max of ti minus di. So if you do the math, you find this, okay. Another question is, what happens if the max, if this is less or equal than 0? Because I mean, this star is something is supposed to be, you know, if this is less or equal than 0, I mean, what happened to this upper bound? Have you any insight, idea? You have no idea. Okay. If you have no idea, I try to help you with the idea. So if the max of ti minus di is less or equal than 0, what does it mean? It means that all ti minus di are less or equal than 0. It means that di is greater or equal than ti for all I. Okay, that's quite clear, right? So if di is greater or equal than ti for all I, then
we have arbitrary deadlines.
No, we're not arbitrary. We have deadline. Arbitrary is arbitrary. This is arbitrary. I mean, it's larger than a period. Arbitrary can be also less than a period. Okay, this is larger than a period, larger or equal than a period. But if we have the utilization less or equal than 1, and deadline larger or equal than a period, and then what? It's scalable, and that's it. We don't need to do big magic, right? So, the task set is obviously scalable because, right? So if the max is less than this, then it's less than equal. Then you know we have all data larger than period. Since I'm using this sustainability to prove something that is obvious, but you know, just to use a concept that exists and is around. Since EDF is sustainable, then right, if yes, if it is schedulable when the data are equal to period, then it's also scheduled when they are larger. And since we have the condition of utilization less than 1, then it is schedulable because we have data equal to period, utilization less than 1. So it is scalable because of sustainability. It is scalable also in all cases with data larger than periods.
Yeah, but in this case, we don't know it is schedulable with deadlines less than or equal to periods.
In this case, we don't know.
If it is the task set is schedulable when deadlines equal to periods. I mean, you know, just by because so when we try to calculate these stars,
when we try to calculate this stuff,
it is negative,
which
means that you really don't know. So you mean to say that you should calculate when d star is equal to d. No. In that case, it is implicit deadlines and yeah. Okay, no.
Okay, good. Good, you did it yourself. Okay. So now, I mean, just to show you what does it mean negative. I mean, of course, well, you know what they mean negative, but you know when you have data that's larger than period, basically the first step of all tasks happens much ahead of time, right? So basically we have the DBF and something like a big first steps and then maybe smaller steps. In this case, of course, if you compute the upper bound and you compute the intercept with the t, you find something negative. So it's no surprise that you know when you have arbitrary data, the d star becomes negative.
Sorry. It has been proved that the critical instant remains the same also with deadline greater than the period.
I think, well,
to imagine.
I think it's proved, but then I have Andrea who always say, well, this is not really proved anywhere, so I don't know. I think it is something assumed to be true with very strong confidence. Okay? Then I don't want to hurt Andrea's sensitivity.
No, but I think it is proved, right?
Is it true?
In Sanjay's paper. So he can.
Yes, it's written by Sanjay. Yes.
I think so.
Yes, I think so. Yes. Okay, yes. Well, there is another quite nice test that is a faster and exact test. It is called quick convergent processor demands. I think it's demands, right? Which was proposed by Zhang Barnes. Well, I think this is much simpler to be explained with the drawing. I mean, while I draw, we go through the algorithm. Let's say that we have, let's make the case of a feasible task set. Or something like that. And so the D star is here. Okay. What does the test say? Well, the test say start from this star and goes backward in time. Okay. I mean, the goal is always to check for some other reasons, we know that for T larger than this star, the DBF is below T, so we are not interested in that. So we're interested in T that are between 0 and this star. So this algorithm starts from this star. So basically, well, actually it starts from the biggest deadline less or equal than this star. So it starts here. Okay, so T is here. So what happens? Check. Look, is it a welfare D mean? Is this? Right. So we start here. It's check. Look, is it the DBF here at this point less or equal than T? And we are, at a larger. I don't know if it should be DBF of T or T. There's something I have to check. It's a mistake. DBF of T, but I have to check. Anyway, this is just a stopping condition. Maybe it's T larger than D mean or DBF of T larger than, I don't know. Anyway, so it's a stopping condition from the while. So what happened? Yes. So if the DBF, of course, if the DBF here is not, then we are out. We are not scalable. So we check, and we go in. So if the DBF of T is strictly less than T, because now we know inside that it is less or equal. So the only two options are if it's strict or not. If it's strict, then we set T equal to the DBF. So basically what we do, we take the DBF here, and we do sort of like this. So here we go at this point. Okay, so we do this kind. So here, we go here. So we do sometimes when we evaluate recurrent function recursively, we do this kind of pattern. So we evaluate here. Right, and basically we continue because here we evaluate, while doing, okay, let's do this. The claim is that from this point to this point, the DBF is always below, which is fine because from this point to this point, the DBF is always less or equal than the DBF at this point. And this we know because the DBF is non-decreasing, so right. But then from this point to this point, T is also above this value. So the condition is guaranteed anywhere at all points here. So we can go and check here. Okay. I mean, the advantage is that if in the case that here there are many steps, we just skip all of them, and we don't need to check all the deadlines in here. So somehow, what we do, while continuing the loop, we do here, here. Then we have T. We check the dBF here. The dBF here is lower. So the next T is going to be this. We are here. We check the dBF here. The next T is like here, maybe. Yeah. Or yeah, something like here. Here the dBF is here. The point. Yeah, I think that it should be T. When T goes below the smallest deadline, then we go out of the loop and it's scheduled. Okay. The observation is that the dBF is always below this sort of envelope that we construct by doing this pattern, while T is always above.
So basically, what you do is at all for each iteration, you find the largest absolute deadline less than the demand bound.
You find the largest
absolute deadline less than the previous demand bound.
Intermediate points are not deadlines.
No, yes, these are not necessarily deadlines. So in fact, here T takes dBF.
Okay. Yeah.
There is one point where you have to do a trick. The only point is when yeah, the second line, escape from the fixed. This is a special condition which occurs in the case where you are when you have a dBF which is touching T. Okay, because when the dBF is touching exactly T, if you do T takes dBF of T, you are stuck forever, right? So you have to go out. How do you go out? Basically, you take the largest deadline strictly less than T. Okay? So at this point, what do? You go here. You take T. So T is here, and with this rule, you would be stuck here forever. But then the escape rule is that here you take the largest deadline below T, which in this case, for example, is this value. Okay? And then here you keep going with the same. Okay, this is a quite efficient algorithm. It works fine when with low utilization. When utilization is high, close to 1, then, well, it's not worse than that, because in worst case, you check all points and you do a bit of loop, but you know the complexity of this algorithm goes high when the utilization is close to 1. Okay, I mean this is something that probably you can understand from the approach to when you have utilization very low. Basically, you have a dBF growing very slowly, right? So when you make the very big steps backwards, so you check here, right? So you go here and then here. So you go. I mean, you make then here you evaluate the dBF. So you make very big steps when utilization is low.
Also the start goes.
What?
Also
and the start also it gets smaller. Yes, I mean of course.
When you have prime periods or co-prime periods.
I think here prime periods has nothing really to do because it's about I think I think the harmonicity of periods does not play a crucial role here. Okay, so this is QPA. Then, of course, I mean, once we have exact tests, I mean, theoretically speaking, QPA is still not polynomial because when utilization is large, it takes actually still quite a lot of time, and the demand of function test does take a lot of time. So, I mean, there is an interest in developing the sufficient test for arbitrary deadline case or constrained deadline case, which help you to find a good solution. Okay, so I mean, maybe the most natural way to apply to extend the test is the so-called density test, where basically you replace the period with the minimum between the period and the deadline. So somehow, if you have a task with activation, like with a deadline, let's say activation and deadline here, and activation deadline here, activation and deadline here, okay? Here's the deadline, is the deadline. Basically, this corresponds to replace this task with something that does. So you have a deadline, and then you bring the activation coincident to the deadline. And you have the deadline, and then the next activation coincident. So basically, it corresponds to reducing the period to the value of the deadline. And this is, of course, more a conservative transformation. So if this is a schedule, then this is also schedule. That's and it's called density. Sometimes this quantity is called density, while Ci over Ti is called utilization. There was also this test, which was proposed by Umadev in 2003. This is still, I think, linear complexity because you can accumulate. So it's linear, right? It's linear. It's linear because you can take advantage of the previous computation. Yeah, so another interesting linear test with linear complexity was proposed in 2003 by Umadevi. Let me write a note about the complexities next time. Okay, and this is, this is not really something that I can give you the intuition of. It's a bit elaborated, or maybe it's not, but I don't remember. So maybe it's simple, but maybe not. I mean, I just don't remember where it comes from. So yes, it's a test. It's a linear. Well, it's a linear complexity. It admits more tasks than the density test, but of course less than the exact one. Right. So another stream of tests are those that are called fully polynomial time approximation schemes for EDF. And basically, these tests are, start from this observation, quite simple observation. They define the demand bound function upper bound of task I, function of t, and also k, where k is what? Is an index of the step at which we stop making steps, if you want. So basically, we have here okay, so this is the DBF of one task. Basically, k is the index of, let's see, if the absolute end of the k, so this is the one, the I1, the I2, the I3. Okay, so basically it considers the exact DBF. Let's say I do the example with k equal to 3. With k equal to 3, it considers the exact DBF at, up to the deadline di3. Then, from this point and on, it approximates with the real function. Okay. So it is function of k because depending on k, it starts from here, 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 and so on. Okay, a nice property of this fully polynomial time approximation scheme is that not only this upper bound is larger than the DBF, this is quite obvious because it's the same up to some point, and here it's something above. Okay, but the bound function is also lower bounded by some, downscaled version of the upper bound. Okay, basically, if you multiply this such that these points goes here, and you see that the coefficient is just k over k plus 1. Basically, you move everything down and you get something like this, 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 right? So if you multiply the upper bound by that term, basically the result of the multiplication is below the DBF. So this upper and lower bound condition allows to assert a quite interesting result, which is as follows. Well, right. So if the totalization is less than 1 and we check the DBF in all points denoted by dk bar, where k bar is the index of the deadline at which we stop checking. Okay. So basically, this set cannot contain more than, so the cardinality of this set is less or equal than k bar times n, okay, number of tasks, because it includes k bar absolute deadline, at most k bar absolute deadline for all tasks. Right, so, and then we have to check if this is less than 3, because for values large, this is guaranteed. It's scalable. Otherwise, that's also the interesting part, the new interesting part. It is not schedulable over a CPU with speed k bar over k bar plus 1. Okay, this is called a resource augmentation bar. So we know that if this condition is sufficient, so it tells us that if this is true, then it's schedulable. However, it also tells us that if this is false, then it's not schedulable over a CPU with a reduced speed by this factor. Okay. And of course, if you make k bar going to infinity, then basically you reduce the gap between of inaccuracy introduced by this step. So somehow, with k goes to infinity, you have this CPU speed going to 1, which is the one where we are performing the test. At the same point, you are increasing the number of points here. So you can trade, if you want, the number of points where you are testing the schedulability and the speed of the CPU on which is guaranteed to be not schedulable. Right, it's called a fully polynomial time approximation scheme.
We got the title.
The title what?
FPPA. It should be FPPA.
Fully polynomial time fully approximation. Fully polynomial FP.
It's
yes. FP, full polynomial time. Fully polynomial time approximation scheme. Let's cross fingers. Thank you. Okay. Yes, right. Yes, today I think it's going to be quite a short class, but I think you don't mind. So, sensitivity analysis. In the same way as we did with fixed priorities, with EDF it makes sense, of course, to consider sensitivity analysis. Just as a reminder, sensitivity analysis has to do with the variation of parameters. So how much can I tolerate an increase or a decrease of deadline periods, computation time, whatever. Okay. Right. So, and this is really analogous to fixed priority. So, in the sense that what is the maximum tolerable speed? Well, that's not that difficult because we have sum of something, let's say, okay, I from 1 to n, We have this number of jobs I at t, ci less than or equal than t. We have this for all t into some set d that depends on a lot of stuff. Then if we want to find a speed, then a speed r means that if we go at speed r, basically we are dividing the computation time by r, and we bring r here and t down here. We transform the for all into max, and we get exactly that. Right? So from here we get for all t, r has to be larger or equal to sum of blah 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 over t, and then for all becomes r greater or equal than the max for t into the set of sum t. Okay, this is what we get. I mean, it's just a super simple math. Right. And of course, and then the minimum speed, of course, is the one, the smallest that satisfies it. So that's why I call R min equal, well, so I call the minimum speed, then it's the one where you have the equal sign. So this is R. Okay. Right. However, we have to consider that when computing D, the set of deadlines, since if we do the upper bound of the linear upper bound of the DBF into the set D, it appears D star, and D star was function of the utilization, right? And now, since we are playing with the speed and we are playing the utilization, computation time, we cannot use that expression anymore because the value of utilization is subject to change. So here we can only use this. We can only use as D star H plus max, the classic, the older value. Okay? So
but I didn't get that. Why do you want to find D star again?
No, the star is needed to reduce the set of deadlines over which you are checking the test, right? So since this star depends on the total utilization and we are changing the slope, then we cannot use it anymore. Okay? Right. And with QPA, performing this test is a bit trickier because you cannot really, you remember those steps that you do with the algorithm? Those steps do depend on the value of the computation time. So it's not that simple to find how much you can change the computation time such that the QPA remains true. So apply QPA for sensitivity is a bit harder. Right. With the very same math, we can compute the maximum feasible computation time for each task. And here there is no rocket science. We just do the same. From the summation, we just take the k task on which you are interested out, so that we isolate. So yeah, we will bring just quick. So we have what for all t sum of I of n I ci and I is a function of t less than or equal to t. Then what happened? We make the sum, right, different than k, and we bring the k term outside. We want to find ck, right? So we bring everything on the other side. So we have ck less or equal than t minus sum on I different than k. Then the rest will divided by nk of t. We have for all t, for this to be true, yeah, then we get that. I'm going to do that right. Just to say. Okay. Okay. Right. Okay, so I conclude with an example. I conclude with an example with these numbers. Let's see if what happened in the schedule, just to recall. So here we have what no, this is a bit long. No, next time I do the schedule in the slide. Okay, so if you compute the response, just as a comparison, if you compute the response time, we schedule it with deadline monotonic, for example. Priorities are in this order. So we find the response time of the third task is 14, as the deadline of 10 missed the deadline. With EDF, what happened with the density test? No way, because density test is computation time over the minimum. Here the minimum is 3. Here the minimum is 8, so 1 over 3, 2 over 8, and 5 over 10. And we get 13 over 12. It's greater than 1. It's close to 1, so there are chances to find some. If you do the Davis test, which is the one that I have that slide, basically we have to do that test for all k. We have k equal to 1, we get something. K equal to 2, we get something that is true. And for k equal to 3, we get something that, well, in the end turns out to be false. Okay, so this is not good either. If we try with the exact test, well, we have the exact test with a set of deadlines, and the value d star, in this case, we do the math is 50. So we have to compute the test up to, for all the absolute deadline, up to 50. And these deadlines are really many. If you do QPA, well, I'm not drawing the DBF, but just to show you what happened. Well, the minimum deadline is 5, right? So here we have, so we start at D star, 50, DBF at 50 is 43. 43, 33, so we do this kind of DBF, and then we set t equal to the DBF. At the end, we get at 9. At 9, we evaluate the DBF is 4. 4 is less than d min. Ah, yes, right, you can check with the DBF too. 4 is less than d min, and then we go out, it's scheduled. So basically, in this case, with QPA, we did 9 iterations. We basically compute, we often use to, as a term of comparison for the complexity, to evaluate how often it's needed to compute the DBF. With QPA, we compute DBF 9 times, while if we had to check for all t, we had to check for the cardinality of the set that I showed before, which is 32. So we should have computed it for 22 times. Right, so here basically I do the test with, let's see, with a fully polynomial time approximation scheme. With k equal to 1, we get this set, and it is not schedulable. So with k equal to 2, we get a bit larger set. So we have one extra deadline for each task, and probably 2 absolute deadlines overlap, so that we have only 5 instead of 6. So we check the test at all 3 points, and it is schedulable. So what information do we get? We get that the task that is schedulable, which is 5. We also know that the task set is not schedulable on a CPU with speed k bar over k bar plus 1 with k bar equal to 1, right? Because for k bar equal to 1, the test was false. So basically, we know that it's not schedulable over a CPU of speed 1/2. Yes, and it's actually concluded yesterday, very short. And this could conclude the class for today. Okay, any other question? Fine. fine. Non c'è la missione.